Yeah. Well, yeah, so these two cancel.
So great there.
Okay, I like that. As long as that works for Kathy.
Yeah.
So if I split these up,
Yeah.
and I'm just going to use the quick notation here.
Not perfect, yes.
I get this here, right? Plus the sum of 27I over n plus the sum of 12 over n squared. Sorry. Like that. Right, distribute that 3 over n through. Okay. And I'm not pointing anybody out, but it is very simple to put the wrong thing in here. Delta x goes here, so there should be no I dependence here. That'll really screw things up, as some of us found out. Okay. Blah, blah, blah. So now I can take the negative 27 over n cubed, and what's the sum of I squared? Yeah. Good. Plus 27 over n squared. The sum of I is the nice little dude. How are we doing so far? So this is from here. That is there. That one's the nice one. 12, yeah, because the sum of 12 is 12n. Cancels with the n on the bottom. So you just get plus 12. This limit here will always be 2. This limit here will always be 1. So you get negative 27 times 2 divided by 6. Negative 27 divided by 3 is negative 9. Plus... Yeah, oh, that's the 6 from there. I'm freaking myself out over there. 27 over 2 plus 12. You get 3 plus that is 6 over 2 plus that is 33 halves. Cool. Now, have you guys done this one? Let's do this one right away, because you'll see this come popping out of here real quickly. How are we doing there? Is that... Cool. So what's the antiderivative of this?
So it's going to be negative x squared, yeah, over 3 plus over 2, 4x.
And again, it doesn't always happen, so don't make this general. But 0 happens to make all the 0. If there were e's, that's the one that always gets people. If it was e to the x, you plug a 0 and you don't get 0. So don't just think, oh, it's 0, it's 0. Make sure that it actually comes out to be 0. So that one does come out to be 0. So all I need to do is plug a 3 into this. And again, not picking on anybody, but it is really simple to just start throwing things in before you actually get an antiderivative. Right? Believe me, it's remarkably easy. And your brain says, well, that was all right. But you got to first get the antiderivative, because that's what is related to the area, which is what the interval is asking for. Right? So get the antiderivative, now I can throw that in, and I get this really quickly. 3 cubed divided by 3 is 3 squared, I get negative 9. When I throw a 3 in there, I get 3 squared is 9 times 3 is 27 over 2, which is there. And here, 3 times 4 is 12. It's crazy. So, of course, I get the same answer.
Well, not there.
Which, again, I love how nobody said anything. There it is. It's not surprising because this process is what this accomplishes. So, of course, at some point towards the end, they're going to agree with each other because they actually end up being the same thing. It's kind of weird. All right. So let's see. Let's do this one right now. Well, you want to do this one? I guess let's do this one since it's related to that same function. Here's what I do with these. Well, first off, what's delta x going to be? 3/4. So like 0.75. So what's x1 going to be?
0.75.
No, I'm using left endpoints.
3.25.
Left endpoints. And where am I starting?
0.
So x1 is going to be 0. Yay. You guys with me? I mean, the first input to figure out a height is going to be a.
Yeah.
If I was using right endpoints, the first input would be a plus delta x. It would be, you guys kind of with me?
Yeah.
All right, which is sort of related to this whole mess here. All right. X2 in this case, so of course, that'll be 0.75 past that. X3 will be 0.75 past that. And X4 will be 0.75 past that.
Or 2.7.
2.25. Because one more step would take me to 3, but I don't take that step because that would be if I did right endpoints. Are you with me? So if you draw these in, now it's easier to draw these in. So the first height is divided by 0 and it stops at 0.75. Bam. The next height is at 0.75 and it stops at 1.5. Bam. The next one is designated by the height at 1.5 and it stops at 2.25. And then the next one, the height is set up by 2.25 and it stops at 3. That's why it makes sense that 3 is not here because the last rectangle has to have room to actually stop where you want to stop. Does that kind of make sense? Because I remember and I know that as a student you're like, I want to go to 3. Why is 3 not there? Because you get there on when you grow that rectangle. All right. Grow your little rectangles. Yes?
Is the width 0.25?
No. Sorry, it's 0.75. Well, 3/4, yeah. So now it's pretty simple. I use this where n is 4 now, right? I use that, and we already, let's see if we can just go straight to it. So in general, I can take delta x out, and in this case I have f of x1 plus f of x2 plus f of x3 plus f of x4. So that times that is the area of the first rectangle, so forth. So I have my 4 rectangles areas adding together. Are you guys decent with this? Yeah. It's the same exact thing I see here. I just factored the delta x out. And again, why does it make sense down here that I could do that? Somebody pointed that out the other day, but hopefully you understand why I don't do it down here. But why should it make sense I could take it out? Because it doesn't have an I in it. So of course I can take it out. Doesn't see me coming. So delta x is 0.75, and now I just got to plug those inputs into the function to see all my heights. Yeah, so what do you the first height is 4. I got that one. 5 point who?
6.
6?
6.2.
6.2?
5.8.
5.8? I don't hear any opposition, so it sounds like those are good. All right. And then what do you get when you plug it in the calculator?
16.2.
Who is?
16.2.
16.2. And if I make this into a decimal, that's 16.5. Why was my approximation so good, even though I just did a left endpoint? Because the interval I'm integrating across, this function is... The function is... Symmetric. So if I had a function that was not symmetric, and the book makes a big deal about increasing, decreasing, what is an overestimate, what is an underestimate. You just look at the damn thing and tell. But they have a good point. If it's always increasing and I do certain endpoints, it's going to be an underestimate or an overestimate. But if the function itself is symmetric, it's like averaging itself out, which you're like, thank you, function. All right. Yes, sir.
So if we're doing the same problem using the midpoint, would you use the delta x3 over 8?
If you use midpoints, delta x is the same. It's just that you would start
From 3 over 8.
Yeah, you would start at you would use the midpoint of those rectangles. So your heights, you wouldn't use these to input into your function. Yeah, you would use 3/8 exactly. The first thing in between these two is 3/8. I like it. So if you did the midpoint formula, it's just the midpoint of these two. I like it. Which makes sense. That's why they call it that. I like it. Good. Is that good? All right. All right. So this feels nice. I like this because you can see it. And then when you do it in the calculator, remember you can put this function in the calculator and have it spit it out at you. And I love the visual when it fills it in. We did that together a few times, so always, if I'm you, that might be the first damn thing I do, so I can see very quickly if I'm going astray. I'm like, it should be 20, and I'm getting 487. Something not right. All right. So we're good there? Let's move down here. So how do we do this? Wow. Good, so I made this one nice. So the antiderivative of this is x cubed plus x, from negative 1 to 3. And how do you do that from there?
Plug in 3.
Good, plug in 3.
27 plus 3 is 3.
Yeah, so 27 plus 3 minus, plug in negative 1. So what I'm doing is f of b minus f of a, what the f-talk says, right? Part 1, or part 2. Is that decent? Because I always get someone, like in Calc 2, they start putting the lower one in first. I'm like, wait a minute, that should just be totally something you can't even do. It just, of course you put the 3 in first. It should just start to become part of your process. And right now you go, I put the 3 in first, because this is what the freaking theorem says to do. Right? Okay, good. I like it. And then when you plug a negative 1 in, you get negative 1 minus 1. Now, and people freak out about the negatives. We should be past that. So you get 30 plus 2, 32. Did anybody check it in the calculator? Oh, well. All right. You did? Did it work out? Yay! It's always good to know if the calculators are programmed correctly. Right? The humans have to check every now and again. Now you know me, and it's not just because I'm evil, but it's because trig is very important in general life. Some teachers teach calc and barely use any trig, and then they take my 280. And then they're like, why are you such a mean teacher? I'm like, no, your 180 teacher was mean, go slap them. So I continuously try to keep trig alive because it is stupid important. You could teach Calc 1 with barely any trig. You totally could. You totally could. And it doesn't mean that it's not important. It's just because you're learning processes in Calc 1. You're not actually learning, like, real life problems. There's problems in your trig. I can just pick the ones that don't have any trig. And then I'm killing you, your future. Alright, that's enough of that. Little PSA or a rant, whatever you want to call it.
And cube 3?
No, that's tangent.
Yeah, what is the derivative of tangent?
Secant squared.
So what's the integral of secant squared?
Tangent.
Tangent. That's the relationship, because the integral is the antiderivative. It's the opposite of a derivative. So if it goes this way, it's got to go right back the other way.
Isn't the only one that's different just sine and cosine with the signs?
Oh, and it's not that it's different. It's just that since the derivative of cosine is negative sine, the integral of sine must be negative cosine. It's I don't know if you guys understand. It's not that it's different. It still has to go back to the thing that you would have taken the derivative to get there. It's just that the derivative has a negative sometimes, so it's going to mess it up. But that's what's going to mess us up. So the more you know the derivatives, the better intervals should be, but you've got to force yourself to think backwards, because that's what intervals are. They're derivatives backwards. Okay. So that antiderivative is completely tangent from 0 to pi over 4. What's the
1 minus 0
tangent of pi over 4 minus tangent of 0?
is 1 minus 0.
Tangent of pi over 4 is 1. Tangent of 0 is 0. Now, stop and think about that. It's kind of nifty. Secant squared is a funky-ass function, but you integrate it from 0 to pi over 4, you get just 1. It's kind of nice. I just like that one. You get weird things and weird values, and 1 comes out. You're like, oh, that's weird. All right.
It's so nice.
I know. All right. Now, this one you might think I was being evil, but I was actually being really nice, giving you natural log limits.
Yeah.
We just talked about how to do this antiderivative. What's the antiderivative of e to the 3t?
E to the 3t over 3.
Yeah, or any way you want to look at it. E to the 3t over 3, or 1/3 e to the 3t, from ln2 to ln3. So I get e to the 3 ln3 over 3 minus e to the 3 ln2 over 3. What is e to the 3 ln3?
9.
No.
3.
No.
3 times 3 is 9. 3 is...
What do you do with the coefficient of a log? You can bring it back up as a Power. So you get
Oh, 27.
27. So it's 27 over 3 minus 8 over 3. Right? 2 cubed is 8.
Ah, yeah.
19.
You guys see what's happening here? Because if I can get that coefficient out of the way, the E and the ln will kill each other. They will kill each other, and I can just pull that bad boy up here as a power. That's why I gave you ln input, so that would happen. So you get
19 over 3.
19 thirds. Cool. Which again, you can check in your calculator on its test. That would be really nice. You can check to see if you get the right answer. Isn't that nice? As long as you put the right function in, you'll be all right. Garbage in, garbage out. All right. So anything about that? Because that's basically going to be what your quiz looks like.
Basic.
Basically.
Leave that there for right now.
Pretty basic. Pretty basic.
So last little thing here.
Wow, today's Wednesday.
Today is Wednesday. I know.
Actually.
Which means I have time. It's crazy. Oh, this is what I want to show you. So if you're one of those crazy, weird-ass people that take a math class and don't even look in the back of your book, I don't understand you. That's the first thing you do when you get a book. So for example, to see what kind of answers they give you for one thing. So they give you some functions, that's nice.
Oh, that's so nice.
And then they give you some logs, notation stuff, and laws and hyperbolic stuff, nifty.
Gosh.
Yes. And then, of course, they give you differentiation formulas. And then they give you... I should have brought my...
Ah.
Yes.
Und Table.
Table d'intégration. Oh. Sorry.
Wait. French?
You almost eat your... Yeah. For the American, I'm going to have a sandwich and look at my table of integrals. But, I mean, some of these look very familiar. Here's the integral secant. And look at the freakiness that it is.
Ah, it's so freaky.
But here's the integral tangent. We proved that for ourselves earlier.
Much nicer.
What's up?
Is that calculus?
Yeah, you must memorize all 100 and... No. But, I mean,
Memorize.
there's these that you should know, right? Because they come from functions that we know the derivatives of. And then there's these that are not so obvious, right? And then, of course, you eventually get to the point where you're like, yeah, whatever you say, book. But we're going to do these by hand, eventually.
You're not going to
Wah,
memorize.
wah, wah.
You mean we're going to draw them
No,
on
you're not
our
going to have
hand
to
and
memorize these. You're going to know the procedures so you can do any integral that I give you. So there are certain procedures that take you from something that looks like this to this. But in my office, I have this red book that is this thick, and a good, I'd say a fourth of the book is devoted to integral forms. So there are these, this table of integrals is like a smidgen of a true table of integrals. And I also at home, I got a little pocket table of integrals just in case you're walking along and you're like, oh shit, I need to integrate. Oh, okay, gotcha. Oh, thank you. You never know what's going to happen.
Quick, integrate these values before I
But it's just good to know these are here. I mean, this is kind of nice. You can kind of look at it and just get a feel for how things work. Some of this is just not obvious, so it doesn't really help you determine anything, but oh well. And some of this stuff is in Calc 2. Some of this stuff is Calc 2 stuff. But a lot of the stuff we're going to learn how to do by hand. All right? Yes, sir. What's up? Oh, dude. Constants that you need in engineering, electricity, and stuff like that, and just a crazy. I can bring it next time if I think about it. It's a good paperweight. Good doorstop. All right. So that's all I got for today. That's plenty. So, I forgot. Study session tomorrow.
I'm going to be there.
We're in our normal room. I think it seems to be open most of the time. 36-345 minutes.
Is that the paint room? Or is that the...
That's the room that's in the building like this on the other side of the science building.
The paint room?
Paint room? Sure.
Smells like paint.
Oh, okay. I didn't even notice. I huff a lot of paint, so I'm just like, it's burnt out. I'm not sensitive to that.
Where are these coming from? Like, I know what they're for, but how do I derive these? Or
We derived the first one. These you'd have to use something called math induction. So for right now, we just say this is what they are.
okay, so should I just memorize them for the quiz?
I give them to you.
Okay.
Yeah.
Because I was worried. It's like I don't think I
Calc 2, you'll be able to prove them. The first one we proved, yeah.